Good afternoon from Finland. A very warm welcome to our VTT webinar, Redesigning Plastics for Circularity. We are very happy to have such a large and diverse audience, and we very much appreciate you all taking the time to tune in today from all around the world. We hope that you will enjoy our presentation, which will be followed by a Q&A session, which I'm predicting it will be quite lively based on all of you online. I am Anna Tenhonen. I work as a senior scientist and project manager at VTT in material processing and circular solutions. My background is in material development, business development, and circular economy, especially in circular plastics, including bio-based alternatives, and my research is focused on sustainable circular economy.
And my name is Holger Pöhler. I'm working as a professor of practice for industrial chemistry at VTT. Before I joined VTT a year ago, I was working for over 20 years in the chemical industry, thereof 15 years in the plastics industry. At VTT, I am responsible for what we call an opportunity, and this opportunity is called circular plastics. So there's a nice fit to the content of this presentation. Before we start with the details, a few comments on practicalities. All of you attendees are muted, but we encourage you to be very active in asking questions via the control panel. We will do the best to answer your questions during the Q&A sessions. However, whatever question we are not able to answer during the Q&A question, we will come back to you afterwards. If you have any problems with the audio, try to optimize your connection. It is also possible to dial in via the phone. Toll dial-in numbers are included in the invitation. We do not only encourage you to ask questions, we also would like to have feedback and comments on our webinar. So we welcome any feedback, and for that purpose, a feedback form will pop up when you close the webinar at the very end. All the material which we present today will be available, and we will send out the handouts after the seminar.
Before we're able to dive into the substance, let's take a few seconds to look at VTT. VTT is one of the leading European research organizations, and we're based out of Finland. We are a visionary partner for research, development, and innovation, and we help enterprises and society at large to put new science and technology into practice. By a vision where a brighter future is created through science-based innovations, and our mission is to help customers and the society to grow and renew through applied research. Our strategy is to impact through scientific and technological excellence. We actually have these 5 global challenges that we have selected that our research and innovation activities aim to solve. We aim to solve these challenges: future climate, sufficiency of resources, good life, safety and security, and industrial renewal. We are a significant international research institution with 240 million euros in funding. We are a major player in Finland. Actually, more than a third of all Finnish innovations involve some of our expertise, and we employ more than 2,000 people. At the same time, we operate in an increasingly international field, with actually 47% of our customers' turnover coming from abroad.
Now it's time to start discussing about the actual topic of our webinar, Redesigning Plastics for Circularity. I hope we can agree on the fact that plastics as such is an excellent material. Plastics are easily be processable, they are lightweight, they are relatively cheap, and they have a major role in our daily lives, sometimes very obvious, sometimes not so well seen. They protect us from injuries in our hobbies or in our cars. They ensure a quality life in many medical applications and even keep us alive in the field of medicine. Maybe the most visible aspect of plastics is in packaging, and they are specifically in food packaging. They keep our food fresh. With plastics, food waste can be prevented or at least delayed, and thereby having a significant contribution to the reduction of greenhouse gas emissions. So plastics is a success story, and that can be seen also of the global volumes produced since plastics became commercial in the middle of the last century. The yearly growth has been significant and is expected to reach even 1 billion tons of plastics per year in the year 2050. So everything is great, or is it?
Not so great, actually. There's definitely a need for change. The great plastics, they have been designed for optimum use and not initially for recycling, which leads to global problems. And I think we're all aware of the challenges related to the plastics, especially the plastic pollution and waste in the environment, like with the ocean plastics. It's a very evident example that we are all privy to. And actually, unfortunately, over 8 million tons of plastics end up in the oceans each year. And this is due to the lack of infrastructure for waste management. Globally, 78% of plastic waste ends up in landfills and the environment. 12% is incinerated, and only 10% recycled in some form. The link between incineration to CO2 emissions and the greenhouse gas emissions to climate change is quite clear as well to all of us. But also the plastic production is rather intense in emissions. And actually today, the greenhouse gas emissions from plastic production and incineration are more than 850 million metric tons. This is equal to the emissions of from 189 500 megawatt coal power plants, which is also actually very close to the total emissions of greenhouse gases in Germany in 2019. If we keep going the way we're going, the current trajectory is that by 2050, the cumulative emissions of the plastic life cycle will be over 56 gigatons of CO2 equivalent. This is 10 to 13% of the global carbon budget if we calculate it based on the 1.5 Celsius degree target. So there are definitely things that we need to fix.
The first answer and correct answer and easy answer is to make plastics circular. So we want to go from a linear plastics economy through eco-design elements and through circular business models towards circular plastics. This sounds easy, but if you look at the problems we are trying to solve with plastics, we find out that the situation is actually rather complex. So let's have a look at the issues we are dealing with. So we mentioned already the plastics pollution, and we mentioned the climate change effect. So we would like to stop pollution, and we would go towards carbon neutrality in the plastics value chain. If you look at plastics pollutions first, a very practical and very useful element of a circular economy is keeping the material longer in circulation, and that can be achieved by reuse business models. This can be applied to plastics as well. There are many plastics applications where reuse makes sense. You are all aware of deposit schemes for bottles or refill systems, which are now offered by many brand owners. However, one also needs to be clear that reuse is only a solution for a limited number of plastics applications. So for all the others, you need a proper collection and separation system in place. Collection is obvious to prevent material ending up in the environment, but also separation and sorting is extremely important in the circular economy of plastics. Plastics is far from being a bulky one-type material, which can be simply collected and reprocessed. It's very important that plastic is not only separated from other waste types, but it's also important that plastic types are separated from each other. If you do not do that, the recyclate value will be low or lost. And only if that is in place, we can enter actually the world of recycling, which is the major element of the circular economy of plastics. Recycling is a broad topic. There are many different technologies available. It can be roughly categorized into mechanical and chemical recycling. And during the course of this presentation, we will explain the details and give a few examples for these different categories. The second topic we touched upon was climate change. So how do we make the plastics economy more carbon neutral? Well, the easiest and most straightforward approach is to replace the fossil feedstock by, for instance, bio-based feedstock, or through recycled feedstock from the above mentioned recycling industries. But also another element will play a major role in the future, which is carbon dioxide. So we rely on carbon capture and utilization technologies. Carbon dioxide is especially needed if you consider the competition of bio-based feedstock with arable land for food and the not completely closed loop in the chemical and mechanical recycling. Therefore, it's essential that we have also carbon dioxide as a source for plastics manufacturing. One element which we will not explain further in the course of this webinar, but it's still worthwhile to mention, is the relatively high energy consumption related to the recycling industries. So we need to make sure that clean energy sources are eventually available, not only for plastics manufacturing, but also for recycling, because it's clear that we don't want to close one, or we want to stop one of the circular plastics elements, the plastic pollution, by recycling. We also need to make sure that the energy which is required for the recycling is coming from clean energy sources.
I think it's clear that there are a lot of different initiatives towards the circular plastics economy. There are EU-level strategies, initiatives, nationwide, as well as different foundation-led initiatives. And there are a lot of efforts to go towards circular plastics. The challenge is, however, that it's a rather complex world of plastics, as the material is used across different sectors in a variety of applications. And the making the plastic circular, it's not trivial. And this drawing here displays the different approaches for circular plastics that we have identified as crucial elements. So here in orange, you can see the traditional linear plastics value chain, where the feedstock is based on fossil resources and goes through plastic production, product manufacturing, the use phase, collection and sorting, and the end-of-life options are mostly incineration and landfill, as we discussed earlier. But of course, there's also the leakage into the environment. But here we are displaying how we see that this linear model can be turned into a circular model. In green, you can see these circular elements, and let's go through these cycles one by one. So the reuse cycle, it's where you reuse the article or product as such without destroying it. And this is prominent and quite promising to produce quite a lot of savings in terms of greenhouse gas emissions and decreasing the plastic pollution in the field. The polymer cycle describes the mechanical recycling, where the polymeric backbone of the material is not destroyed, but the product, however, is. And then to go to the monomer cycle, it shows the chemical recycling, where the material is taken back into the building blocks altogether. So the polymer structure is changed. Then if we look at the CO2 cycle, let's look at the technical CO2 cycle first. So this is going to be a very prominent future feedstock. So taking CO2 from air from next to factories and capturing it and utilizing it as a feedstock for new plastics. And then if we take a look at the kind of the bio cycle, so for example, compostable plastics, it's also a viable route on how to circulate the material. We must be very specific about the conditions of biodegradation, as they determine the speed and degree of degradation. So it's very important to be sure here that how the materials degrade. Basically, from the biodegradation route, we get biological CO2 cycle, like we have named it in the biological CO2 cycle, and it must be important that this is balanced so that the CO2 in the atmosphere is not exceeding and contributing further to climate change. So that's where the balance between the technical CO2 and the biological CO2 comes into place. But also from the biodegradation route, we get material like soil, which further can be used for production of bio-based feedstock. So the photosynthesis uses both the CO2 from the air and the soil. But it's very important to highlight that there is no one-fits-all solution for plastic circularity. And the sustainability needs to be looked at from all of the angles, and we have to think what is technologically, economically, ecologically best approach on a case-by-case scenario, most cases. There are wide different range of factors that we have to take into consideration when making these kind of circularity assessments. For example, the plastic type, waste volumes, general infrastructure, regional climate, available energy. These are just a few of those that have to be accounted for in if we do life cycle analysis or circularity assessments.
General introduction to the topic of circular plastics economy. I'm sure that many of you are aware of this, but I think it's important to lay this fundament for the further discussion and also to illustrate what VTT is doing in the different solutions for circular economy. We have now put together a number of examples that show you our activities in this field. It has to be said as a disclaimer that this list is neither prioritized nor complete. We have many more activities in the field of plastics, and it should just give you a taste and should act as an appetizer for the variability of solutions that VTT has to offer in the field of circular plastics. We are very happy to discuss with you into more details and also other solutions if you are interested.
Yes, one major challenge that we have identified is that for reuse businesses, especially if we think about business models where we have, for example, food containers that we use again and again and again, they typically suffer from wear and tear. They get scratchy, the material degrades, which makes the products brittle. These are challenges that are faced with the reuse models. We want to extend the useful life of these plastic materials and products. But how can we do that?
At VTT, we have many activities in this field. Self-healing surfaces or repair by trigger is an important element of circular plastics, and also VTT is active in this one. We are developing currently different approaches for surface repair. We are using cross-linking or chain extension technology to achieve this. And our latest development in this field are multi-use reversible surface repair solutions. As you can imagine, I mean, if you can fix a surface once, this will increase the lifetime of the article by a factor of 2, which is a good achievement. But if you can do this in a reversible, repeatable format, this will be of much more value. So this is something we are working on. We are also working on a bio-based self-healing agent. You see here an example of how a scratch on a surface of a material after UV and heat treatment has all but disappeared. The market we see for this is not only limited to plastics. We have tried this surface treatment also on other materials like glass, and we believe this can be extended to many different areas. We expect this to improve plastic deposit schemes, food packaging, surface coating. The TRL level for the solutions which are available within VTT are low to medium, but we have proof of concept for all of these technologies existing, and we are very happy to find a partner to develop this technology further.
Another issue is that the traditional linear plastics, they have been designed for performance in a make, use, dispose economy. So there is no built-in incentive so that these materials would be easy to recycle and easy to circulate. So this concept of eco-design has taken a lot of interest across the field. And how we see it is that there can be this digital design to help material circularity. So we know that different plastic types have their own performance specialty. one type can have excellent gas barrier properties, the other has very good moisture barrier properties. But then a third type of plastic can have the proper strength properties. And another one, for example, has good adhesive properties that are needed for the solution. This has led to multiple material solutions that are difficult to recycle. For example, with food packaging, there are these multi-layer, multi-material solutions that have been laminated together into very thin films. And these laminated films are really challenging to separate from each other. So it makes inherently the recycling impossible. So to fix this problem, we need to start making the plastics fit for circularity, and it's a big endeavor. And the material functionality needs to fit the circularity and this requires material development. But the material development pipeline can be very long, and it can take a very long time, and it can be rather expensive also if we, for example, do this material development by only experimentation. So at VTT, we believe that the power is in material modeling. And already now we have the structure property and property performance models available that allow virtual material testing and prototyping. But the beauty of what we're doing is that we don't only look at the virtual material design of building blocks for performance, but we also take a look at how the material can be degraded and what is the fragmentation behavior of these materials. And this is very essential for circular economy and polymer degradation, because we really need to make sure that we provide new, better solutions that are sustainable, that don't further contribute to these challenges that we're trying to solve, like the plastic pollution. And Holger, can you explain more about this proper tune solution that we have?
Yes, at VTT we are using integrated computational material engineering platforms already for a while for hard materials like metals and ceramics. Our platform is called ProperTune, and it integrates different length scale models like Anna was just describing for structure property relationships and property performance relationships. This allows us already now, as I said in the mentioned field, to design and develop new materials. But we truly believe and have indications that this modeling approach can be also applied for polymeric materials. We believe that design of high performance materials, and we have shown that, reduces the product development time by half. It allows us systematic optimization of wear, fatigue, and fracture resistance. And as Anna mentioned, it's extremely important also to understand the degradation mechanisms of materials in a circular economy, and the modeling approach helps us also there. So we are very happy to offer this modeling tool as one of the technical solutions for material design at VTT.
Then if we continue with another major concern, as we know, the plastics, we have a wide range of different applications, a wide range of different polymers, and even a wider range of different additives that are used with the polymers to form the plastics. One very big challenge is the heterogeneous varying in quality of feedstock. So especially for the mechanical recycling, the effect of inefficient sorting and polymer degradation during reprocessing is something that is of concern. And this leads to both low quality recyclates and eventually breaking the circularity loop. And this is something that we have also thought about how we could overcome.
At VTT, we use an approach which we would call smart recycling. What we do there is, after collection, sorting, and pre-treatment, which is done in a very traditional way, we reprocess the solid plastic waste through a first extruder. At the outlet of the first extruder, we measure the rheological properties of the polymer, feed it into a second extruder, and at the outlet of the second extruder, we measure the viscosity of the outcoming polymer melt. And all this information is fed into a controller, which can do several things. First, we can feed virgin polymer to make up for the feedstock variations. This is already in use. Another approach is to feed compatibilizers to improve the mixing of different polymeric fractions. This is already in plan and will be realized soon. And to completely close the loop in terms of controlling the effects of degradation, we would like to also extend this technology in feeding chain repair agents to counteract the effect of degradation and repair the degraded polymer chains. This is at the moment still in the planning change, but we believe that this approach will help us to achieve a better recyclate quality, a better recycling rate, and while we are improving sorting and separation, we are less dependent on ideal plastic fraction separation. However, even though while we are constantly improving mechanical recycling technologies and the amount of plastics that can be recycled mechanically will increase in the upcoming years, there will always be fractions of plastic waste that is not suited for chemical recycling. Either it's too mixed or it's already too degraded for the physical recovery of the polymer change. So mechanical recycling is not really an option for these routes. In these cases, chemical recycling offers a feasible outlet. There are many different chemical recycling technologies. They have all in common that the polymeric backbone of the plastic is destroyed. This can be achieved in different ways. We have here from relatively pure streams the possibility of a depolymerization. This is a relatively benign chemical recycling route, which gives us neat monomers. However, it's also limited to certain types of polymers with heteroatoms in the chain, for instance, polyesters or polyamides. Unfortunately, for the majority of plastics, this route is not applicable. For instance, polyolefins are better suited for thermochemical recycling technologies as pyrolysis and gasification.
Yes, I think pyrolysis is being looked at as a very promising technology to solve the chemical recycling challenge, and it's looked at to enter the markets quite soon. And what VTT has actually done, we have a very strong know-how and background of many years in thermochemical processing of different types of a wide variety of bio-based feedstocks. But what we started to do some years ago is we started to apply this to pyrolyzing plastic waste. And you can see an example here of a flow diagram of one of our catalytic pyrolysis reactor setups. And we at VTT, we actually have a state-of-the-art infrastructure from lab to bench to pilot scale. So, but to take a look at this flow diagram, just to kind of give you a basics, the pyrolysis is a process where the material is chemically decomposed at elevated temperatures in the absence of oxygen. So the feedstock is fed into the pyrolysis bubbling bed unit, and then it's further processed at the fluid catalytic cracker where we can optimize the yield for wanted products. And the products that we do get out of pyrolysis are, of course, char, waxes, but the most important ones are the oil and the gas. But of course, we also are looking at these rather side stream like the waxes, that what kind of optimum uses we can have for them. And the TRL level of this catalytic pyrolysis reactor is currently around 5.
Another thermochemical recycling technology where VTT is very strong is gasification. Not too different from pyrolysis, it enables the recycling of mixed plastics waste, which are containing organic and inorganic contaminants. The traditional gasification process yields syngas as a product, and syngas can be then used, or is a very feasible and viable intermediate for other materials as monomers, chemicals, liquid fuels, or for the energy sector. More and more, we are focusing on the conversion of polyolefins to olefins in the process of gasification or other recyclable hydrocarbons. The picture you see here is a commercial gasification plant which is already running, built by Stora Enso in the city of Varkaus in Finland and developed based on VTT technology.
Now, if we jump from the recycling technologies and material innovations to look at the feedstock challenge. So we all know that we need to shift from the virgin fossil feedstock into renewable feedstock. We need to address the climate change issue. And but the challenge is typically that how do we create high-performing plastics from bio-based feedstock? And VTT's vision is to utilize the forest and food waste streams that don't compete with the food production. So taking the sustainability there into high account. One really nice example is actually our awarded bio-based packaging solution, where we have coupled two cellulose-based films together. So we have this thermoplastic cellulose and nanocellulose film that have complementary properties. The thermoplastic cellulose, it actually provides the moisture and water vapor barrier properties, and then the nanocellulose film gives the oxygen, gas, and grease barrier properties. The solution is 100% bio-based. It's recyclable in extrusion. We have actually tried that we can loop it back into a film 6 to 7 times. The thermoplastic cellulose, it also provides heat sealability since it's the outer and inner layer, and the nanocellulose film is in the middle. So the thermoplastic cellulose provides heat sealability, but also printability. And we can also process it from several different types of raw materials, as long as they are sufficient in fractions in terms of mainly the limiting factor being lignin content. But this allows to use a wide range of bio-based local resources that don't compete with the food production, for example, agricultural waste, or of course this wood cellulose that we have been using so far. This solution is also processable with the existing machinery. So whether we're talking about material production or the product production. So we have done different types of films, blow molding, injection molding, 3D printing. So there's a wide range of possible applications for these products as well. And we actually have received quite many awards for this solution. So in 2018, we were announced as one of the winners of Circular Materials Challenge held by Ellen MacArthur Foundation, and we received $200,000 to take this solution further. Then we won also the Sustainability Awards Bio-Based Packaging category in 2018, held by Packaging Europe, and even one more. So we won the EcoPack Challenge in 2018, which was held with Packaging Innovations in association with Marks & Spencer. So this is where one really cool example, what kind of solution with high performance we have developed. And another example is, for example, this PEF that Holger will explain a bit more about.
Yes, Anna, we have a number of applications at VTT in the field of packaging. And we can only select a few which we present here, and one of them is based on a solution which is using food waste streams to make food packaging material out of that. It's exactly the PEF you mentioned, polyethylene furanoate. You all know PET. PET is one of the most common plastics for food packaging. It combines excellent barrier properties, good mechanical properties, and it's easily processable, but it's mostly fossil based. The question is there a bio-based alternative available which shows similar performance properties? And the answer is yes, it's exactly the PEF. PEF is bio-based. It's based on the FDCA monomer, which is given here at the right-hand side. It shows better barrier properties than PET. It has a lower carbon footprint than PET. The mechanical properties are also slightly better, and it's also very well processable. There are commercial routes through FDCA through PEF. Mostly they are also bio-based, and they go through HMF as an intermediate. We have our own technology on FDCA that allows us to exploit a unique synthesis, which goes through a very stable intermediate aldaric acid to FDCA. We believe that this is one of the major benefits our route has over the alternative processes. We have this currently at kilogram scale available, and we are very happy to develop this technology also with a partner to full commercializations.
Thanks, Holger. And I think it's time for us to start wrapping things up and to conclude the different types of elements that we have described. So basically what we want to do is we want to take the single-use plastics and especially look at the reusable plastics route. But how do we do that? We need the molecular repair technologies, and we need the refurbishment as ways to support the reusable business models. We want to take the non-recyclable multi-materials into recyclable, in some cases, if possible, mono materials, but make them non-recyclable recyclable. And for this, we definitely need to have better polymer design. To overcome the low quality recyclate challenge, we want to, of course, turn these low quality recyclates into high quality recyclates. But then again, the elements to do that, we need novel material identification and sorting. And we need to counteract the feedstock variations and degradation. We need to look at how we can provide an outlet for these mechanical recycling rejects. We need to be able to have these recycled, and we're looking at chemical building blocks from these through chemical and thermochemical recycling. Then again, we are looking at the virgin fossil-based feedstocks, where we want to make the shift towards renewables and have the plastics being made from renewables. And of course, the renewable feedstock is crucial here. But in addition, the CO2 from carbon capture and utilization is definitely going to be an interesting trend in the future. Then finally, the plastics that are not currently recycled, we need to see what kind of alternative routes there are. Are they biodegradable, or can we make them recyclable in some way? And into this factor, we have to take in many elements into consideration. So the polymer development and the biodegradability and recyclability assessment needs to be crucial in turning this plastics that are not currently recycled into recycled materials.
I think there are a number of takeaway messages. I think we gave you a quick tour de force of the solutions that VTT has to offer. We could not show you everything, and we could not go into very much depth either, but I hope we were able to show you the variety of solutions we are offering and the technical applicability of the solutions that we are providing. A few takeaway messages. We believe that there is not really an alternative to circular plastics economy if we want to maintain the benefits of plastics in a sustainable way. But at the same time, it's also important to understand that there is no silver bullet for circular plastics. As Anna was describing, we need to very often do a case-by-case analysis to find the best solution for a specific plastic type and a specific waste type. In order to design the material and make sure that the material is suitable for circular plastics, we need to use the power of computing in order to make it faster and cheaper. Material design through computational methods will be the future in material development. Efficient sorting and separation was already highlighted, is of paramount importance for the high quality recyclates, But this is at the same time also supported by smart mechanical recycling technologies. So while the sorting and separation gets better, it's also important to make the recycling technologies less sensitive towards varying feedstocks. Chemical recycling at the moment, only a small fraction in the whole world of circular plastics economy, will gain significant relevance if we want to further close the loop and increase the recycling rates. And we have a number of solutions to offer there. And last but not least, renewable carbon will play an essential role from biomass, from recycled feedstock. Carbon dioxide in the future will make to help plastic carbon neutral in combination with the transition towards renewable and clean energy.
Thank you very much for your attention. It is now time for the questions and answers session. And we have actually received a ton of very good questions from you guys already, but please keep on putting those questions in through the control panel. And we will be very happy to answer them. Like we said in the beginning, if we don't have time to go through all of these, we will get back to you afterwards. But Holger, let's dive into these questions.
Let's do so.
Good. So many thanks again for a lot of very good questions. And let's kick off with a good one. That Holger, what do you think? Is it possible to have a full-scale gasification process that can transfer polyolefins into olefins?
Yes, this is actually a very relevant question. I think we got a number of questions around that topic. So let's maybe try to combine them a bit and try to structure this a bit. So first of all, yes, it is possible through gasification and through pyrolysis, through thermochemical recycling to recover olefins from polyolefin plastic waste, or recover also other monomers in thermochemical recycling. What is the most preferred way to go? I think that's what we are trying also to make clear in this specific presentation is very often to be decided on a case-by-case scenario. So if we have a very polluted, very mixed stream, then the preferred route, if you want to use thermochemical recycling, is go through traditional products like pyrolysis oil or syngas in the case of gasification, and use this later for the manufacturing of other products, for instance monomers, to close the loop. But of course, if you have rather clean streams, polyolefin streams, I think then this is a very viable route, feasible route. Maybe to clarify a bit, I mean, we had this picture with a TRL level number 9 there on the slide on our gasification process, which VTT has developed. This was actually a traditional gasification process, but we are working also for many years now also on the gasification of plastics towards monomers. So in short, the answer is yes, but you need to look at it on a case-by-case scenario. And then there is a bit on the sustainability.
Yep.
Yeah, okay, there we get a lot of questions now in here. Okay, so
I think maybe if we want to address a bit the kind of the overall sustainability, I think we're getting a lot of questions in terms of that and comparing it to the energy and maybe also the capital intensity between the mechanical and chemical recycling, and also a lot of interesting questions regarding these matters as the CO2 feedstock.
CO2 as a feedstock, yeah, okay. Yeah, carbon dioxide as a feedstock is, of course, I mean, and that was correctly, I think that was coming in as a first question. It's a very, let's say, energy intensive route. But then again, I think we also need to see that technology is developing. At the moment, carbon dioxide maybe doesn't play a major role as a feedstock for plastics. But I believe with technology development, I think it becomes an important element. Not, of course, for all plastics, but I believe, and we believe at VTT also strongly, that carbon dioxide is an important element of a circular economy of plastics, it cannot do everything, but it is an important element. Then on the overall sustainability, capital intensity, of course, I mean, mechanical recycling is energetically the preferred route. I mentioned this already, but if you truly want to close the loop and want to increase the recycling rates, I think we must focus on chemical recycling, and it will play a major role, and thermochemical recycling will play a major role. I think there are also other players in the field who have shown interesting LCAs. I think just to mention BASF has shown a very interesting life cycle analysis that chemical recycling, thermochemical recycling is actually a feasible route. We are getting so many questions. Maybe we and one comment. I mean, we will come back to you with all of the questions. We probably won't be able to answer everything here, but we will get back to you and answer each of your questions.
Yeah.
But maybe Anna, if we look at something for you, so I think we get a general question there: is plastics recycling at all economical?
Yeah, it's a big question, and of course, a big piece of the economical aspect is, of course, the comparison to barrel oil prices and the feedstock there. But a major kind of point in this frame is also the legislation and the policy framework. So the different targets, the different mandates, restrictions, bans that are being set, they of course dictate quite a lot that what has to be done. If it becomes a question of will your business be viable, can you actually operate, then the economical aspects are of course very much different. If we take a look at, for example, these mandates that you have to have a certain amount of recycled content in a product, then of course that will drive the market for recycled content. So it's most likely not going to happen by itself that the kind of economics of plastic recycling would kind of fall into place as it is. But there's a lot of that goes on behind the scenes, the legislation, the policy framework, and I do think it also comes down to the simple fact that we just must do that. It's a must that we somehow must address the climate change, but also the plastic pollution. So we cannot just keep on ruining our environment.
Right.
I think, Holger, let's take this one for you. Does your improved extrusion technology apply to different types of polymers?
Yeah, we get a number of questions also around that topic. Yes, yeah. It can be applied to different types of polymers. I cannot tell you too many details here in this public seminar, but we are very happy to go to discuss the technology with you further if you are interested. It is, I think there were also, let me just check, to control recyclability. It seems as you have another process which increased the cost of recycling. I think that's a good point. Of course, if we add a new element, and which is actually a matter of process control to the technology and feeding virgin polymer or chain repair agents to the process as such, it makes the process first a bit more complex. But we believe that how it always is with new technologies, when these technologies become more mature and become more mainstream, and we believe that this is the way to go for mechanical recycling. If you want to increase the recycling rates in mechanical recycling, then the cost factor will not be the determining element. Of course, it makes it at the beginning more complex, but eventually it will fix a lot of problems. Okay,
yeah, I think maybe adding to that also that you get higher quality recyclates out of the process. So of course there's added value in the product as well. So the price, of course, is a bit different.
Right.
I think maybe a follow-up to. Do you want to add?
Yeah, I just picked up one, but
yeah, I picked up another one relating.
Yeah, in a way, I think we have a bit on trying to combine a little bit like comments and questions. So composting, recycling. How do you see that, Anna?
Yeah, it's of course it's always a case by case assessment that we need. For example, I think Nova Institute is doing really interesting work currently on defining useful applications for biodegradable plastics. And there are clearly these applications where it makes sense, for example, agricultural plastics to have biodegradation as a property, but it always needs to be assessed case by case. And I think it's important that we realize that with the bio-based plastics and the biodegradable plastics, we don't just do the single-use plastics again, so we cannot target that the plastics are single-use. So it's much more valuable to keep the material in flow as such. And I think also just comparing the composting to recycling, it doesn't reflect the whole sustainability picture, because of course once the polymeric material is degraded, it is lost, and new material has to be created and processed so that we can turn it into products again. So it's a very challenging thing to compare those two from the sustainability point of view directly. But I think it's always, again, we come down back to the single fact that it's a case-by-case assessment, and we have to look at it from the application point of view. What is the best solution?
Yeah, there's a question maybe which also fits quite well to what you have been doing, Anna. The cellulose packaging looks amazing. What do you think it will be start being used by companies, and how long does it take to degrade at the end of its life cycle? So it's a bit related to this also.
Yeah, it's something that we are working on. We're working on currently, so we are scaling up these different solutions for the thermoplastic cellulose. So if we look at the solution, it has two different types of materials. So we have the thermoplastic cellulose, and then we have the nanocellulose. And the thermoplastic cellulose, the biodegradability of it's quite slow. So for example, with the nanocellulose, then again, we can degrade it in approximately 30 days. So there are very different types of applications that they could be used for. And for the application that we combined for the Ellen MacArthur Foundation competition, somebody asked about the properties about it. So the nanocellulose of it, I'm talking about the water vapor transfer rate and the oxygen transfer rate. So the nanocellulose, it has very good oxygen transfer rate properties. It's around the same as cellophane. And then the water vapor transfer rate, it's a bit more poor for the HEF cell or the nanocellulose, but once we combine it with the thermoplastic cellulose, that has around 6 times better properties than PLA. So together they make a quite nice solution. And of course, that's just an initial application that we did. We have not targeted in yet per se to optimize it for other solutions yet. But we have interesting projects going on, and of course we're very excited to see it enter to markets, hopefully in a few years at least. So it's a matter of just scaling up the applications, and I would say that we're in pre-piloting scale, going towards piloting for the material production and the product manufacturing.
Right.
Yep. But we ask one from here about the surface repair solution, Holger. What about the food contact in your surface repair solutions?
Yeah, of course. I mean, the idea of this this surface repair solutions is to make, for instance, deposit schemes more interesting, and so in that sense, I think it would be very interesting to apply this also for food contact materials. I have to say that at the moment we have been mainly working on applications which are not from the food sector, and also like applications which are not even in plastic. So that we have been actually treating other surfaces, but and there of course we are most advanced in the development. But we believe, and we have already work ongoing on also finding cross-linking agents or chain extension agents that could be applied also in food contact. However, we are not necessarily applying for any, let's say, food contact or food approval. So this is something which then needs to be done together with a cooperation partner or with a brand owner or whoever is interested in the technology. But we believe that this technology has a much broader applicability and works quite nicely in the context of circular economy through useful life extension. Okay, now we have let me just check. Okay, so we have been covering. There are of course some questions which are very much detailed, so we will come back to you. I mean, there are some technical questions which we cannot answer, or some of questions actually I cannot answer also because I don't know, but I will look this up. But I think what we have a little bit on the I think maybe if you comment, Anna, a little bit on these pledges which are ongoing.
Sure. I think there's a wide range of different pledges that are ongoing. I think the Ellen MacArthur Foundation initiatives are, of course, quite well known by many. And one thing that I do like about them is that, for example, this pledge called Line in the Sand, it's a commitment that is dedicated to the whole value chain of plastic production. Mainly packaging sector is involved, but they basically commit that by 2025, all packaging would be recyclable, compostable, or reusable. And there are other pledges also that the companies can have made, and they also promise that they will provide annual data on their progress. So I think that's something that we might be missing a bit on what is the actual effect of these circular economy initiative strategies, that what kind of effect that they really have. So that's really important. And I know there's quite a lot of discussion on also the sustainability of circular economy. So not always these circular economy solutions are sustainable. So getting more data on that, I think it's very, very interesting to see. But of course, I think the biggest one directing the activities within Europe is the EU plastic strategy also. And there we have the different alliances and pledges also. So I think there's a lot of activity, and I'm really interested to see that what kind of results we get rather soon.
Yeah, we have, I just went up a little bit, two questions maybe which we can quickly address. Also, one is the major issue for recycling is low density and linear low density polyethylene, which is where current recycling levels are very low. What plans do we have, or do you have for these? Yes, it's true. I think polyolefins in generally, I think the recycling rates are not so fantastic. And I think we believe that we have a combined approach there. I think mechanical recycling as well as thermochemical recycling can help there to increase the recycling rates, and we have solutions for both. Then a question directly after that, maybe that is also, does polymer design make sense unless you have the opportunity to separate and sort it from other plastic materials in the waste? I don't know, Anna, do you want to answer, or?
Well, I think it does make sense, and it's not just about the biodegradation, but also the degradation of the material. So if we think about, for example, reuse models where you want the product or the article to last as long as possible and have it look nice, then you can model in that how does the degradation affect the material in terms of loss in mechanical properties, for example. But I think it comes back to maybe we can tie in a few questions on the collection. Does it make sense? Also, if we look at chemical recycling, there we can expect that the chemical recycling should not be a priority against the mechanical recycling. So once we have the rejects from the mechanical recycling or materials that are not being mechanically recycled, then we can look at chemical recycling, where, of course, if we can also divide the feedstock further based on efficient collection and separation, that could be interest, of course, but also there's the advantage of having a bit of more acceptance toward a heterogeneous waste stream for these chemical recycling solutions. And I think if we link it back to, there's a good question on bio-based packaging, recyclable by extrusion. How do you have to collect that waste? Bio-based plastic could be a problem in the recycling loop or the composting loop. you are absolutely right. I think there's currently the composting standard is being reviewed, so the regulations affecting the composting, because there have been a lot of micro and nanoplastic discussion around improperly degraded materials in the composting loop. So that's definitely a big issue. And I personally, I think we should always look at the recycling loop if possible before we go into taking the material apart altogether. But then again, the issue becomes on the volumes of how much material we have and what is sufficient to recycle. But maybe on a quick note, it can be a problem, but also we have quite nice, interesting results on recycling bio-based plastics with conventional plastic, where it actually improved the qualities of the conventional plastic. So it's not always that it's a bad case. It can also sometimes have positive effects. So this is again comes back to the fact that we have to really assess things case by case, and it's really hard and not the best to do generic conclusions about materials in this economy.
I think we are running out of time, and it was actually a really interesting discussion. So I think first of all, maybe thanks a lot for this very relevant questions, and we will come back to you with answers. But we also asked you, by the time that the seminar is over, you will get a what was it, a feedback form or something like that, and you can give us feedback there. Also, I think our email addresses, Anna and mine email addresses, are given in the document you could download when you registered to the seminar, and the material will be made available also to you afterwards. So I think these were the formalities. Is there anything I forgot, Anna? I think this was
no, just when you answer the survey, after it will pop up on your screens. If you have any additional questions, you can also ask further questions that you didn't have time to type at this
absolutely
moment.
And we will get back to you, if not tomorrow, but within reasonable time we will get back to you.
Yes. Yeah. But thank you everyone for your time.
Yeah, thank you very much for your participation and your active questioning. I'm sorry if maybe the answering of the questions was difficult because there were so many questions coming in, but I think as I said, and as Anna said, we will come back to you, and we'll hopefully give satisfying answers to your questions. So thank you very much and have a good day.
Thank you.